Hello everyone, this is Darren. I'm just going to be going through our second tutorial now. You can find the code for that on our GitHub page under Unit 2 Equivalence Trials. And just like before, we should see a number of things here. We have the raw RMD file that you can copy and paste into your RStudio setup. And you can go ahead and look at the overall tutorial as it's rendered into a markdown file. Okay, so just to come over here, so what we're going through here today is this basic idea of an equivalence trial. So we've got some of this in the lecture, and I just want to recap some of it here while we're looking at the code from the tutorial. Getting our head around how an equivalence trial works, which includes both non-inferiority, which is what we usually see out there, and non-superiority. Those two things together lead to our understanding of equivalence. It kind of flips our normal hypothesis testing procedure on its head. So sometimes it can be a little bit tricky to try to figure out exactly what it is that we're doing. And so here we've just got a set of code set up where we're going to first go through frequentist confidence intervals. This is where we left off on the last tutorial. We did how to do p-values, how to use those for binary significance testing, hypothesis testing, where we're interested in controlling for type 1 and type 2 errors. Now we're going to talk about confidence intervals. And once we understand confidence intervals, then we're going to turn around to using them as a tool for doing equivalence tests. So just like before, we're using RMD files. You know what those are now. This is code I've just copied and pasted. And so one of the nice things about working with code is that as you develop more and more of a library of your own code that you've used to produce documents, then you start to reuse your code and reuse your functions and everything else. And next thing you know, you're doing things a lot faster than you've ever been able to do them before. So the same deal here. I've got the same code here to install my packages that I'm going to use for this particular tutorial. And then just going down through here and talking about the confidence intervals. And confidence intervals, I'll add a few more things here, can be very tricky in terms of their interpretation. They're quite confusing for most people. And most people kind of overinterpret what they mean. But the basics of confidence intervals, they're still a frequentist tool. And that means they're still based on the idea that we have some sampling distribution that we would generate under some null value, for instance 0, and that we want to understand that sampling distribution, and then we can have the tails of that distribution where we declare values that would be very unexpected if our null model was true. And so then the inner part of that distribution, in this example, this would be a 95% distribution because it covers 95% of the space underneath this sampling distribution. And then the 5% is contained in the two tails, 2.5% each tail. So basically, this is the idea of a 95% confidence interval centered on our null. And then all we have to do in order to think about it in terms of the effect size we estimate is just slide that interval over to the effect size we observed. So here, for example, if we did a study and what we actually saw was an effect size of 2 standard deviations, that was the impact of what it was that we did, then we would calculate our confidence interval around that, and that then would give us essentially what is a range of values where if the data had been generated under a model focused on one of those values, we would fail to reject the null for that value. Does that make sense? So here, if I were to set the null for 2, not at 0, but at 2, if I set it at 0, the value 2 falls outside of this distribution, just barely, and so I would reject this null. If I set my null at 2, well, this is right in the meat of my interval, so I would fail to reject this null, and I would fail to reject this null, and I would fail to reject this null, and so on and so forth. So a way to think about a confidence interval is it's kind of what some people refer to as a compatibility interval. It gives me a series of values that my data are pretty compatible with. However, technically, the confidence interval is still just a collection of tests. So sometimes people see confidence intervals and they want to say something like, well, there's a 95% chance that the truth is contained in this interval. And that's not exactly true. It's not true, period. That would be a Bayesian interpretation of what's called a credible interval, and we'll come to that later on in the term, where we can make those kind of conclusions. Instead, what a 95% confidence interval does is because it's a frequentist tool, it still has to be based on this idea that if we were to repeatedly do the procedure that led to our confidence interval, let's say a 95% confidence interval, then 95% of the time our interval would capture the truth. But for any one interval, usually we only have one interval, the one we're looking at for our data, the truth is either in there or not. In other words, we're not evaluating the probability of a hypothesis. We're still evaluating the probability of data given the hypothesis. So we can't interpret it the way that most people want to naturally interpret them. So that's enough for confidence intervals. You can go through this. And again, one of the things to point out is we're getting very complicated with the plots we're doing. So I'm going to pause here, and I'm going to add, I think, a ggplot tutorial overall because it's a really powerful tool for us to use to do a data analysis, and I'll say it over and over again, that anytime I get stuck into any analysis whatsoever, I'm always looking at data. And so here we start with our call to ggplot, and the first thing in ggplot always needs to be a data frame. And we mentioned what a data frame was last week very briefly, which is essentially a structured matrix with some metadata attached to it for things like the names of variables, etc., and where we have each row is an observation, each column is a different characteristic or variable, and that's represented as a data frame in R. So the first thing I start with is this first data frame I've made, where I've just created one variable that contains two values, 4 and -4. And then I set the aesthetics, which is how I start to map numbers or variables onto the visual parts of a graph, like the y-axis, the x-axis, color, and so on. And we'll see a lot of examples. Like I said, I'll put up a tutorial for this in general. People want to see one. So we have the call to ggplot, and then we start to add things. And so one of the things I'm going to add in this particular graph, for example, which is this normal distribution here with a fill, kind of a purple fill there. We're going to limit the x-axis to go from -4 to +4. We're going to add some labels to the x and y axis. This kind of changes up the overall look of the plot. And then I'm going to add on top of what I've already got here. So if I were to just do these things here, I would wind up with something that looks like this. And then I'm going to add the same idea here, stat function, but now I'm going to do just the right-hand tail and then the left-hand tail by setting the limits here. Right, so here, when I did this, the limits went from -4 to 4, but now I'm setting it from 1.96, which is my critical value if I'm using a normal distribution. And so therefore, we're to add those two things, then they would appear like that. And importantly, ggplot respects the order. So the lower something is, then it's on top of the things that come before it. And then I added error bar and the title. And that gets me to the overall thing. Right? So this is a 95% confidence interval centered on the null. Now what I've done is I've taken this entire plot, all this code, and then assigned it to an object called G1, and then I've called that object. So if I were to get rid of this, execute this code, Control Enter, now we don't see anything happen. We see it over here in our environment. Now I can just put my cursor on that line, Control Enter, and recall that object, and there it is. So here then what I've been able to do is then I start with the plot we just had, G1, and now I'm going to add more stuff to it. This way I'm not having to do chunks of code that run up 4 and 5 bits of the page. So now I'm taking G1, which we've already seen what G1 looks like, and there it is. And now I'm starting to add another distribution here, and the same idea where I shift it over. And now I've added in this second bit. So all of this came from the plot from before, and I just put this on top of it with another error bar, which we just discussed. So then we come into equivalence testing. And so again, like I said in the lecture, and I'll say now, equivalent means that we're trying to test both non-inferiority and non-superiority. Now in practice, we're usually interested much more often in a non-inferiority test. That means we have two different treatments usually. One of them is the standard care, but it might have some characteristics that are suboptimal, like it has lots of side effects or it's very expensive. We have a proposed alternative treatment. And while we don't think the new treatment is better than the existing, we might be willing to accept some level that's a little bit worse because it has other good characteristics, such as having fewer side effects or being less expensive. So there's a trade-off there that we're willing to accept. So that's what we're trying to do with a non-inferiority test. but we usually do it with a two-sided confidence interval that at the same time can test for both non-inferiority and non-superiority. So we talk about them together quite a lot. So you can read through what's going on here, but I'm just going to summarize. If we think back again where we started earlier in this tutorial, we have a distribution of our test statistic, whatever that is, the parameter we're estimating. We have a distribution of that under the null value, 0 in this case, and a confidence interval. We can shift that over to what we're going to call our margin. Our margin is this amount by which we're willing to accept the new treatment being worse than the current treatment. All right, so here we're going to say the margin is 3. Now, I've shifted over my 95% confidence interval in the sampling distribution like we did before. And here what I would have is a two-sided test of superiority. Is this better than that? And so if I had values that fell outside of here, then I would rule out that 3 is probably an improbable data generating mechanism, and I would accept that something else was probably the truth. But we don't want that. What we want is a one-sided test, because really what we're trying to look at is this. We want to set up a situation where our null hypothesis is that the value, the truth, is greater than or equal to 3, and our alternative is that it's less than 3. All right, so this is a one-sided test because it doesn't matter to us how big this value gets in theory. It would still not reject our null of our value being 3 or more. Right? The only thing that's going to lead us to reject the null is if we get a value here that's much smaller than 3, so much smaller than 3 that we would say it's inconsistent with the idea that this is the sampling distribution under this value. And so would be values that are incompatible with this idea that the truth is that the difference between the two treatments is equal to 3, that if we saw the data we actually see in our study, this is what, and we did that many, many, many times, this is what that sampling distribution should look like if that was the truth. If we see something out to here, then that gives us some sense of evidence that this probably isn't correct. So this is our one-sided test. Now, importantly, in this example, when we talked about our two-sided tests, here this is 2.5% of this distribution, this is 2.5% of this distribution for a total of 5%, right? My rejection region is a total of 5% of the distribution. Here I'm using one tail, but I'm keeping it at 2.5%. That means for this particular interval, this one-sided interval, it is a 97.5% confidence interval, all right, with one tail out to infinity and the one to here. And that's important. We'll come back to that in a minute. So that's our first test that we want to do. That's our non-inferiority test. And one of the papers we have in the reading describes our equivalence testing as using two one-sided tests, or a tossed procedure, which is a very useful way of thinking about it. So now what I'm adding is the non-superiority test. Here what I'm saying is that I want to start with a null hypothesis that my value is either -3, which is the other end of our margin. Here it was 3 for the non-inferiority. For the non-superiority, we'll set it for -3. I want to know if my value, if the truth is this value or smaller. So again, I don't care how small it gets out to here. I wouldn't reject overall this null hypothesis. I'm only going to reject it when I get a value that's out into the right-hand tail of this distribution. So this is one-sided test. This is a one-sided test. Both of them have an alpha level of 2.5%. And so then what happens is we can take this bit here, this part of this interval that's going to this side of the distribution, this bit here, all right, so that's that and that, and we can put them together. And so we put that there, we put that there. This creates, from the two one-sided 97.5% intervals, it creates a two-sided 95% interval. All right, so this is exactly the same as a 95% confidence interval. We've just come about it from a very different direction. And the logic now is this. If I were to take this 95% interval and I shifted it, in other words, my estimate, if I moved everything to the right, eventually this tail of this confidence interval is going to cross into my margin, my non-inferiority margin. As soon as that crosses that non-inferiority margin, it also means that I've dragged this point estimate so that it crosses into the acceptance region of this test. So when this 95% confidence interval, the upper limit of that, crosses this margin, that's when I can no longer feel confident about declaring non-inferiority, and we'll probably have to say that the data would be consistent with it being an inferior treatment. It's the same thing here if I were to drag this confidence interval this way. As soon as the lower limit of the 95% confidence interval crossed over my non-superiority margin, then it would mean also that my point estimate here would cross this line into the acceptance region, and so we would have to conclude that we had a superior treatment because it would drag this below 0 at the end of the day. So that's how we do and build these tests, equivalence tests. And it doesn't matter. We can, if we only are interested in non-inferiority, it doesn't really matter. We can just ignore everything on the left here, and we just focus on where this particular end of the confidence interval lands. Now, through all of that, one other thing just to touch on is that we talked about type 1 error rates. Oftentimes people by convention set it at 5%, and you will continuously set it at 5%. But the important thing here, though, is that you understand if we're doing a superiority test and we want to have a 5% type 1 error rate, then that gives us a 95% confidence interval. We're still using the same 95% confidence interval, except one really important difference. Here, because it's made up of two one-sided tests, and those tests together represent what's called a closed testing procedure, each of those tests we're using 97.5% one-sided intervals. That means each of those tests has a 2.5% error rate. That is the overall error rate for the two-sided 95% confidence interval in this instance. So let me say that one more time. In a normal superiority test, the type 1 error rate for a 95% confidence interval is 5%. For a 95% confidence interval used to test these two one-sided hypotheses, the type 1 error rate is 2.5% for the 95% confidence interval. That means if we really want a 5% error rate, then we need to use a 90% confidence interval, because then that includes two one-sided 95% intervals. So some of that stuff is talked about in the papers, and if I've muddled it up and haven't clarified things, please get on the discussion board and we can talk about that a bit more. Just coming back to ggplot for one more minute, again, we've kind of continued. You can see how we're building. So here we added, again, some more of these normal distributions. We've added vertical lines. They have characteristics like colors and line types and sizes and so on. So part of using ggplot, just like everything else, is just practice using these things, having a play. So you can come in here and you can highlight some of this stuff. You can change some of this stuff and see what it does. And you can always just, if you see something you want to know, hit a question mark and say stat function, and then the help will come up, and then it's going to tell you exactly what's going on there. All right. Finally, what I've got down here at the bottom is an example of an analysis of a small study where we're looking at fentanyl and morphine for pain control. So you can go through, you can actually load these data, this simplified data set, into R, and we can have a play. A few things here. So now I'm using a new function called read CSV. One of the nice things about R is that if there's a data format, there's almost certainly a package out there in the world that will help you read that into R. Unlike other proprietary software, sometimes that can be very difficult. So here I'm creating a data set. I can look at different information. I can look at the names of the data set. So here I know it's going to be subject, arm, and a bunch of things called pain score. I have a thing called subject. If I were just to highlight this little bit and hit Control Enter, I would see that it's a list of numbers, one for each row, but I could test or double check to make sure that the number of unique data subjects. So that's unique data subjects, and then the length gives me how many of those there are. I can ask if that's equal to the number of rows in the data. So if I were to do a piece, run that code, it says true. All right, so just real simple stuff where you set up these logical statements using the double equals. It's just asking, is this the same as this? And it is in this case, and that means that each row has its own unique identifier. Simple stuff, but the kind of stuff we need to double check. And then I can use a very common function called table to look at this variable. So when we want to declare a variable within a data set, we use the $sign. So the data set object is called R, and then we are specifying which of the variables. It was called arm. So data $arm. If I were just to highlight that, then I would see these are the different assignments of the people, morphine, fentanyl, and so on. And I can make a table of that very easily, a very simple table. So I have 15 observations assigned to fentanyl and 16 to morphine. So to look at the data, we have it in a wide format, which means that when we actually look at it, which I can do here, data, I can click on that. It means that I have one row per person, and that their pain scores are measured over time. So they're measured at time 0, 5 minutes, 10 minutes, and so on. And we call this wide. A lot of times for plotting, we want to switch that to a long format. And so to do that, we use this function called gather. And it takes a data object or a data frame as the first object, the first argument in that function gather. And then it wants me to name the things I want. So instead of having a bunch of columns with the pains at different times, I want 2 columns, one that gives me the pain and one that gives me the time. And then this is just cleaning up some of the variable names. So the first thing I could do, you could just show you what this does. All right, so this is going to take our wide data set like we had before, and now it's going to say, now give me the time. So for person 101, at time 0, their pain was 10. All right, so I could scroll down here, and eventually I get to the pain. So here's 101 again, and this is their time 5, and their pain score was a 9. All right, so you can see now the data set's a lot longer. Here I've used something we haven't used before, and this is called a pipe. And what a pipe does is it takes the object. So this by itself, this is an object, and it sends that object to the first argument of the next function in the list. So normally I would have a data frame in this first space, but I don't because it's implied by the pipe. So I'm creating a data frame. I'm taking a data frame, data. I'm creating or modifying that data frame, which just creates a new data frame with this verb, with this function. And then I'm sending it to the first position here without having to actually type it in. And it's mutate where I'm going to change something. I'm changing this time variable to remove the underscores and the letters. So it leaves just numbers, and then I'm converting it over to a number. So if I were to execute that entire thing, now you can see I've got this nice long data set. Head just means give me the first several rows and show them to me. All right, so just a quick look at the data. Now, what I really want to do, the reason I did all of that was to start to look at the data. Like I said before, and I will over and over again, always want to look at the data. So the first thing I'm going to do is I'm going to create some summary statistics from my data. So I'm using, again, a function called group by. So I'm taking this data set I created called pain. Here it is. I'm grouping it by arm and time. That means I'm taking all the observations from the same arm at the same time point, and then what follows is going to be executed in those subgroups using this other function called summarize. So group by these two things, time and arm specific, and then give me the median pain value, the upper quantile, the lower quantile, the mean, the standard deviation, the number in each group. And then from this information, I can calculate a standard error of the mean and an upper and a lower 95% confidence limit. All right. And then I can spit all of that information into a long data set again. So if I were to do this and execute this code, so I've created this thing. We don't see anything. We just created it's over here in our object. And so now what I have is I have arm, time, and what type of statistic, and then here the median. So for the fentanyl arm at time 0, the median pain is 8. All right, so for time 0 for fentanyl, the upper quantile there is 9. All right, and so on and so forth. And the reason we've reshaped the data like that is when we use ggplot, we need to map individual variables onto different aesthetics I've mentioned before, things like the x-axis, the y-axis, and so far. So what I've got here is I'm going to have a ggplot with this pain data frame I just created. My x-axis along the bottom is going to be time. My y is going to be pain. And then I'm going to use box plots to summarize other aspects of. And then I'm going to use these lines to highlight things like the mean across time in pain in the two groups. And then I'm going to use two separate facets of the plot, one for each group, each arm. So again, we can just start to put this together a little bit at a time. So here I'll do the lines. Right? So I've got the upper, the mean, and the lower quantile. So if I were just to do those bits of code there, I'd wind up with something like that. And it looks weird. And the reason it looks weird is because I don't have them split into two different groups yet. So I had up here when I did my summaries, I grouped everything by arm and time. I don't have arm reflected anywhere in my code up to this point until it gets to here. So if I run that now, it splits it into two things. Okay, so that is the kind of summary information about the groups. And it also includes the actual points where the data are. And this is an important principle in trying to display data. We don't want to just rely on summaries. If we can see the raw data, and we almost always can, even if there's lots of it, we can use tricks to actually visualize all the data. And we want to do that so we can actually see what's going on. So here, if I just finish out the rest of this stuff is just prettying things up a little bit, adding labels, changing the axis ranges, and so on. And then we wind up with a plot that looks like this. And so you should be able to see this is the fentanyl group, this is the morphine group, this is time 0. They start off at relatively similar levels, similar distributions of pain. It comes down for both groups, as you would expect, but the degree to which the data comes down for the fentanyl group is quite a bit lower than it is in the morphine group. And that's what we're interested in, because in this particular study, the fentanyl was intranasal, so it was easier to administer in a tricky group, in a tricky environment. All right, so now we've seen the data, and we want to go through and we want to do some of these two one-sided tests. All right, and so when we use this two one-sided test procedure, what we can see here is this kind of a result. It gives us two different confidence intervals. The 95% two-sided confidence interval we would use for a null hypothesis significance test, and then the two one-sided interval, which is a 90% confidence interval. So for both of these things, the type 1 error rate is 5% for the reason we discussed above. And what we can see here is the mean difference is minus 1.4. So that means when we compare fentanyl, the new thing, against the existing thing, morphine, on average, the mean pain scores in the fentanyl group are 1.4 units less than the scores in the morphine group. And we can actually see in this particular instance that we were willing to accept that the fentanyl scores could actually be worse, right? Up to this level, just over 0.6. So if this 90% confidence interval had gone over that line, we wouldn't be able to declare non-inferiority. But because that confidence interval doesn't cross that line, we can declare that fentanyl is non-inferior, not worse than, appreciably, than morphine. But we can conclude something else here too, because again, this is a closed testing procedure. At the same time, we can evaluate if there actually is superiority. And so here, we have the 95% confidence interval we can fall back on now for this difference in the means, and it doesn't cross the null value of 0. So not only would we declare non-inferiority, we would reject a null hypothesis. There's no difference between the two things, and generally feel pretty happy concluding that in this particular study, the difference was actually better in fentanyl, not just non-inferior. Now, this is a nice way to do this, to give you one little thing, but we can also go through the rest of the code. What it does is it uses the same test here, which is essentially a two-sample t-test with unequal variances. we're going to do the exact same thing, except we're going to apply it to every single one of the different time points. To do that, again, I've come back to a thing where I'm creating a function using this function. I'm setting that it's going to take 1, 2, 3 different arguments in that function and also accept arguments from the other functions it uses. I'm assigning it this name, t-test res. I can't remember why I called it that. And so this, what happens then in these brackets is what this function is. So what's it going to do? It's going to take x, whatever that is. It's going to paste it, and that is to combine text. It's going to paste that to this text here, this little tilde arm, and then it's going to reflect it as a formula. And a formula is a special type of object that's used in models in R. Then it's going to do a t-test on that thing here, form. All right, we're just using the next thing. I'm going to do a t-test using that formula on the data that I've done at the confidence level that I want. Because I want to make 2 tests, right? I want to do a 95% interval and I want to do a 90% interval. And then this tidy function just takes these results and then makes them into something a little bit easier to work with. And then I'm going to modify some of that stuff again to make a prettier result. So all of that happens in this function now that I've created. And then I'm going to do another object now. I'm creating an object type called a list, which is just, think of it as a container for information. I'm creating one with nothing in it. It's empty. And then I'm using a for loop, which we can talk about later. But a for loop, basically what it does is it reiterates the code inside the brackets a number of times based on some conditions that you set inside the for loop. What this says, it says for I in the numbers 1 through the length, which is how long the number of names from some particular data set. So I'm taking data with my pain scores, I'm selecting a number of them, the ones that have pain score and the actual name of the variable. I'm taking those names, I'm getting the length of that, and so now I'm creating an object. So let's just look at that real quick. If I do this, I gotta make sure I get the number of things correct. I think it's 2 of them. If I run just that bit of code, you can see it creates me a data frame with just the pain scores. I can then take the names. That's a completely different object, and it's just going to give me the names of the pain scores, and there they are over here. If I took the length of the names of the pain scores, there's 8 of them. And then if I wanted 1 to colon that, it gives me 1, 2, 3, 4, 5, 6, 7, 8. You see how we're building up here? And now my for loop is going to say use I as some variable. Set it to 1, so now this would be 1, the first position in this list that I've created up here. 1, do this function we just created and put the results there. And in pain score in the first position, 1. So this I is a 1, and then once it's done, it goes back to the beginning, it goes to 2. It does this again where the I's are replaced with 2's. It does it again with the 3's. That's a for loop. So I'm just iterating through the different pain scores, running a t-test and saving the results. And then I do the same thing, except now I set the level to 0.9 instead of 0.5 in this this function I created up above. Right, so I can do this, and that should all run. And so then if I just click on this object and hit Control Enter, you can see here what I've done. I've got the estimate, the first group, the second group, so this is the difference between the 2 groups. I've got the actual t-statistic, and I've got a p-value here, as well as the confidence level low, the confidence level high for the difference, and the confirmation. This is a Welch's 2-sample t-test, which means the one with the unequal variance. Right, so I've done a test for each one of the time points with this bit of code, instead of having to repeat myself over and over and over again, or run a bunch of these. And I can find a similar way to do something with this as well, repetitively. But I like to bring my stuff in the ggplot, and so that's what I finally have done here. Again, we're using ggplot on these sets of tests, and essentially what I'm doing here is creating this plot. So I've got a point range here. The black bit is my 95% confidence interval. The white bit in the middle is the same 90% confidence interval centered on the same point. I've got the 0 difference, so in every instance, my point estimate is that we favor fentanyl, that it is results in lower pain scores on average at every time point post-treatment. Importantly, we want the scale of these time points to be correct. We don't want them all smashed up over here. We want the difference between 60 and 120 to reflect that, because it helps make the plot more easier to interpret. I've got my two margins here. This would be my non-superiority margin. This is my non-inferiority margin. This is my non-superiority margin. I've got that, and then you can just see this. This is the 10-minute result. This is the same thing we had up before with the toss procedure, right? Minus 1.4 with a 95% confidence interval that does not cross 0, and a 90% confidence interval that also doesn't cross 0, and thus doesn't cross the non-inferiority. But it's the same for every time point. And this shape here, right, this corresponds to what we saw before, right? We saw the fentanyl group, the average, dips down lower quicker, and then comes under here. Except now, instead of looking at the two groups separately, I'm looking at a difference between the two groups. And that's how we should always make inferences between two groups. We should never look at the mean in group 1 and the mean in group 2 and say something. We should look at the difference in means between the groups directly and look at the sampling distribution for those things, the confidence intervals for those things. So anyway, all of this entire plot is generated by this code here. There's different horizontal lines. That's what geom H line is. There are the point ranges, which give us the point ranges, which are these things, these like error bar looking things here. We have a rectangle, which is setting the color to white. So it helps us visualize where results would favor morphine versus where they would favor fentanyl. We're adding some labels here to the X and Y axis. We're setting up our time so that it's correctly labeled and has the right scale. And then we've added a little bit of extra text here so to make clear this favors morphine, this favors fentanyl. All right, and then we can save it as well. So we've saved it as a nice high quality PDF that you could bop into a presentation or like that. And then finally, the last thing, and I'll let you run this code for yourself and have a play with it, is that we also create a table that's got the same information. So at each time point, so here then I have the two groups, group 1, and then we can add a little bit more if we put this into a Word document, but I've got the mean, the standard deviation, the number for the first group, fentanyl, and I've got the same information for the second group. And then here I've got the difference, the estimated difference. Here it is for minutes 10, which we knew that was our primary outcome, minus 1.4, just like we saw before in the toss procedure and we saw before in the plots we just made with the right confidence interval. So everything adds up. And this is another really important thing just from the practical aspects of working with data, and I'm sure I'll talk about this other times, that it's almost never where I do a project or do an analysis where I don't find things I've done wrong at least once. And so if you get to the end of an analysis and you haven't found mistakes, then probably there are mistakes you just haven't found. It's not that you haven't made any. And so I like to look at things a lot of different ways, especially because I'm working with other people. They put a lot of time and effort into collecting these data. I want to make sure that I'm respecting their time and effort. I'm respecting the patients. I'm respecting the fact we're hopefully doing important research that's going to improve patient outcomes. And so I try to take this very seriously. And one of the ways to do that is looking at every possible way of chopping up the data in terms of consistently seeing the same results over and over and over again. Okay, so I'll leave it there for now. As ever, if you have any questions, there's a little challenge here at the end where you can go back and use some of the code from this tutorial and the last one and see if you can meet the challenge, so to speak, if this is something you want to learn more about. And again, ask questions on the discussion board. Let us know what you need. All right, bye.